Now, this is an example that is applying the alternating test, applying the absolute test, the absolute value test. So it's an alternating series where the sign changes from term to term. So the absolute version of this series is just given by this, right? So you just write down all the term without the negative sign. So this is an absolute version of the alternating series, and you can prove this series to be convergent by mapping it to a function of 1 over, I think here, x squared, right? So we have seen this already. It's a p series with p equals to -2, and then we have seen that for such kind of p series, when you apply the integral test, then this p series would converge, right? So that means the alternating series here converge absolutely. Therefore, the alternating series converges. Now, let me just repeat for the last time. We are looking at this alternating series, and we want to know whether this alternating series converge or not. So this is the original alternating series. In order to check its convergence, we check its absolute convergence first. Checking the absolute convergence just means you just take all the terms with the positive sign without carrying the negative term, the negative sign in the definitions of the alternating series. So after that, then you look at the absolute versions of the alternating series and ask yourself whether this absolute version series converge or not. So you can prove its convergence by using the integral test. So the integral test, which has been shown earlier on, says the 1 to infinity, it converge, okay, it converge to some number. So if the proxy functions converges, then so is this absolute series converges. So this absolute series, if it converges, then by theorem 6, the alternating series also converges. So that is how we prove it, right? So once we have proved this, then we go to the another example, which is slightly involved. I think in this case, we are actually not seeing an example where the series change sign regularly, right? So you have sine 1, sine 2, sine 3 divided by n squared. So you have sine n over n squared. So you make n to expand. We actually do not know what is the sign in general. So the sign may change from plus plus minus minus plus minus minus plus because this is n, right? N takes on integer, right? So anyway, these terms, this series is an alternating series. It's alternating series, just that it is not a regularly alternating series because the sign may not change regularly from one end to another. Okay, you can plot out the graph and see it for yourself. So anyway, the alternating series here, it's an alternating series, and in order to prove the convergence of this alternating series, what you do is just consider the absolute version of the alternating series. So the corresponding absolute series, the absolute versions of this alternating series is just sine of n divided by n squared, where you just don't care about the sign of it, right? So now you have a situation of sine 1, sine 2, sine 3, sine 1 over 1 plus sine 2 over 4, and then you compare this term by term to this series. So the convergence of the absolute convergence of this series is not quite straightforward. You have to think of a tricks, right? You compare this sign. Let me try to write it out in another slide. So you have a situation of sine n over n, right? So n is positive, so you have sine 1 over 1 and n squared plus sine 2 over 2, where you just take the absolute values of it, and then you have plus sine 3 over, I think here is 4, then you have 9, right? So you look at this series, and then you compare it with, right? So just compare it with what? With 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over, I think 16, blah blah blah, right? This term has a sine 1 in its denominator. This term has a sine 2 in its in its numerator. Then this term has a sine 3 in the numerator, and you know that for whatever n it is, the absolute values of sine of n must be always same or equals to 1. It could not exceed the values of 1. The sine of a functions always limited to -1 and 1. Therefore, the absolute values of sine will always be less than 1. So this term must be less, sine 1 over 1 must be less than 1 over 1. Sine 2 over 4 must be less than 1 over 4. And sine 2 over 4 must be less than 1 over 9. Sine 3 over 9, I said it wrongly. Sine 1 over 1 must be less than 1. Sine 2 over 4 must be less than 1 over 4. Sine 3 over 9 must be less than 1 over 9. And if you have another sine 4 over 16 must be less than 1 over 16. Therefore, it is quite straightforward to convince yourself that the sine n over n is term by term less than 1 over n squared. Right? So you have to convince yourself that this is indeed the case. Right? So this is a series which we already proven to be convergent. Right? So if this series converges and the absolute values of this is less than this one, then when this converges, then this also converges. So this is just like a situation where you have a term that is like 1 over n squared, and it converges. Then you have another term which is sine n over n with absolute n squared, which is lower than 1 over n. So this is a series of sine n over n, and this is a series of 1 over n squared. So term by term, the values of 1 over n is larger than sine n over n. So if the series above the sine n over n converges, so is sine n over n converges. Okay, so we prove the convergence of sine n over n squared by comparing it with 1 over n squared. Right, so this converges, then this term which is less than 1 over n squared necessarily converges as well. After saying all these arguments, what we have tried to say is that these terms, this alternating series converges absolutely. Right? It's considered as absolutely convergent. Therefore, this alternating series, since it is converging absolutely, it converges. Right? So we have none proven what we want to find. We are asked what is the convergence status of this alternating series. Then we said this is proven to be converged absolutely. Therefore, it converges according to theorem 6. So that is this logical argument that is using the absolute convergence as a tools. Okay. So up to this stage, we have already discussed these applications of absolute convergence. Now, together with the absolute convergence test and also the ratio test that we have discussed in a previous lecture, these two tests would then be used in the checking the convergence of power series in the next topic. So when you study the absolute convergence of these topics, you have to bear in mind that this is to be used for the power series. Okay, so I think that's it for this morning. Now, for information, I will continue to make recordings for the power series offline, so you don't need to follow me, but I will do it maybe later today after I take a break. So we'll stop the recording here. And for those who are interested to do that, I think I won't